Well, welcome back everyone. I hope you're able to grab some lunch. So we will shortly begin the fourth session of today's forum. Before we do so, let me just remind you of what we said at the start of the day. I hope you're finding the webinar software works for you. You can leave at any time and join back at any time. That won't affect anything. You will all remain muted throughout, but you can ask questions. Use the question function on the right-hand side. You can also use your phone to dial in with the numbers displayed in the audio tab. And if you have any technical issues, then please contact colleagues on LTES@IRENA.org. Hopefully it's going smoothly so far for you all. So let's begin then with session 4. Now, this session is focused on systemic innovation in energy demand and consumer behavior for long-term energy scenarios. Now, as I think we all appreciate, innovation is at the heart of the global energy transition and is being driven by a variety of trends, but such as digitalization and decentralization. It's important to remember, however, that innovation is more than technology. Rather, it's the systemic innovation that combines innovations in different dimensions, including business models, in market design, in the ways in which systems operate, the ways in which consumers interact with that are creating the solutions that are enabling those significant changes. Now, in this session, we hope to discuss how we can better represent those complex trends and those emerging innovative solutions in our long-term energy scenarios. We'd also like to explore how long-term energy scenarios can help policymakers consider that highly uncertain impacts that system innovation may have. So to help us do that, we have 4 distinguished speakers, each of whom is going to provide an introductory presentation before we move to some questions. Do everybody please use the question tab in the webinar software to post your questions. So our first speaker is Ron Benioff. Ron is the International Program Manager at the National Renewable Energy Laboratory. Ron, I hand the floor to you.
Great. Well, thank you, Paul, and thank you, Asami, and the whole IRENA team. And it's wonderful to have such a robust audience and to stay connected during these challenging times. I really appreciate the opportunity to share some of the relevant NREL work on innovations in distributed technologies and how they're affecting long-term energy scenarios. I'll cover a few different perspectives, looking briefly at sort of distributed generation, and then a look a little more detailed at the demand side based on an electrification future study that NREL completed the first phase of, led by my colleague Drew Mai. So starting with that, the next slide, looking at some of our work. Yep, there we go. Some of the work that we've been doing looking at pathways for power system transformation. NREL recently completed a study in partnership with colleagues in Colombia and India and Germany and other institutions, looking at what's the future of different pathways for power systems, and identified sort of 3 fundamental choices that will vary very much by context. In certain regions of the world, in certain jurisdictions, there's going to be a heavy emphasis on a distributed energy resource revolution, and I think across almost all systems, there will be greater participation of distributed energy resources. Coupled with that will be much greater interactivity between the bulk transmission and the distribution interface, and this will be, flexible modern grid linked with optimized distribution systems, dispatchable generation, real-time monitoring. And at the same time, major changes in bulk power systems, going to very high amounts of renewable generation with storage and with very advanced control technologies and engineering solutions. And underlying all of that will be a very distributed transactional future So this is one where we will be shifting from utilities managing a few generators with passive demand to many generators and control points, active demand that's participating, bilateral interaction with automation, with real-time energy markets and peer-to-peer transactions. And in this report, the links provided there, we've identified these 7 key factors that can influence which pathway is appropriate for the local context, and have developed a screening tool. We're glad to work with partners around the world on use of that screening tool. We also did some expert analysis of what are the technologies that are likely to have the greatest impact on future power pathways, and that's shown in the graph to the right here. So technologies such as blockchain, which will have a huge impact on market transactions and peer-to-peer transactions, energy storage, low-cost solar, but also EV charging, electric vehicle charging and grid services, and microgrid controllers are some of those that we anticipate having the greatest impact. So if we move to the next slide, I'd now like to dive in a little more into the Electrification Future Study. This was and you see the website there, nrel.gov/EFS. This was a multi-lab study, so NREL, Lawrence Berkeley, Oak Ridge, and other partners, the Electric Power Research Institute, universities, Department of Energy, where we developed expert scenarios linked with consumer adoption models, especially for transport and buildings, and economic modeling of the whole U.S. system for electrification of end uses. And what you can see here is through this analysis of the U.S. That we expect, because of electrification of the end use sectors, that electricity consumption will grow 20 to 38% from the mid to the high scenario. Compared, the reference baseline assumes almost no change in electrification, of a very slow sort of continued increase. This increase in electrification is dominated by vehicle electrification, especially light-duty vehicles, with an increase of 11% of electrification to 84% in the high scenario, so a very dramatic growth. This is by 2050. We also see a dramatic growth in buildings electrification, especially space heating, going from 17 to 61%, water heating going from 26 to 52%, and cooking from 34 to 94%. Smaller but significant increases in electrification for industrial technologies. These would be technologies for curing and drying and process heating that will improve productivity and reduce costs. So if you go to the next slide, we looked at, all right, what does all this mean for hourly demand and impacts in different regions? And here you can see, so each circle here represents the top hourly demand, and the wedges show the distribution of the top 100 hours of demand. And you can the net effect in this analysis is that peak demand in aggregate grows by about 33%, which it's a little lower than the total annual increase of electricity as a percentage of consumption, which is 38%. So there's some efficiency savings, and we're also flattening the peak. This is influenced the most by space heating, and so it's the heating sector that's having the biggest impact on peak demand. And you can also see some very interesting dynamics in terms of changes in not only the size of peak demand in certain regions, but the seasonality. So, for example, in the Northeast in the U.S., peak demand shifts from summer for electricity systems to winter as we go to electrified space heating, and so that has a dramatic impact on scenarios and planning and design of electricity systems, understanding these future dynamics and changes in peak demand. Now, wanted to look a little more, if we go to the next slide, at some of the impacts on electricity consumption overall. So in aggregate, the total electricity consumption will be down by 21% for all scenarios compared to the reference case. We're gaining significant efficiencies as we move towards electrification in these end-use sectors. The share of electricity as a supply to meeting energy demand doubles from 20% to 40%. So that has obviously profound implications for increasing supply of electricity to meet this rapidly growing demand. And the share grows significantly for all sectors, but slowest for industry. And we're seeing, but especially if we look at vehicles and at buildings, we're seeing an S-curve type adoption with very rapid exponential type increases that's common across other technologies in energy and telecommunications, and then a slowing increase over the later years. Now, finally, I wanted to say a few words about an exciting new initiative that's a related effort. And so if you go to the final slide, this new initiative is a global power system transformation consortium that NREL, in partnership with many other institutes, the ASEAN Center for Energy, OLADE in Latin America, CSIR in South Africa, Fraunhofer Imperial College, IEEE, EPRI, ESIG, the Energy Systems Integration Group, with the CEOs of system operators around the world, Australia, UK, Ireland, US, Germany, Denmark, and others, are putting together to share best-in-class knowledge from the system operators that are at the forefront of managing both very high amounts of renewable energy, but also an increased amount of very distributed generation and demand management and smart controllers on their system, and also anticipating greater amounts of end-use electrification. So this consortium will provide deep technical assistance to developing countries, coordinated research across countries on these challenges of high renewables and distributed generation and demand management, and support for workforce development, university training, local technology standards, and open data and tools. And we're very interested to partner with others. Maybe I'll just go to the last slide so you can see my contact information. But please get in touch with me if you'd like to learn more about the consortium or the studies that I talked about previously on electrification of the US and on pathways for power system transformation. Thank you.
Thanks very much, Ron. I think that gave us an excellent insights into how some of these things might be changing. Let's move now to, we have a number of questions coming in already, but we're going to save them until we've been through all our speakers. Let's move now to Deger Saygin. Deger is director at the SHURA Energy Transition Center in Turkey. Deger. Can't hear you, Deger.
Thank you very much. Yeah,
excellent.
I just unmuted myself. Thank you very much, Paul, and thank you to the IRENA team for the invitation to speak at this panel. So I'm working at the first and only think tank of Turkey working on energy transition issues, and I'll be giving some insights on a study we carried out together with the Ministry of Energy and Natural Resources of Turkey on EV integration in Turkey to 2030. So next slide, please. Turkey is a large producer and exporter of passenger vehicles in Europe. However, as of now, it has a very limited use and production of electric vehicles, mainly focusing on electric buses, actually. And in terms of electric vehicles, there's only 1,500 EVs, including plug-in systems, being used in Turkey, with an equal number of charging stations. However, Turkey has set a vision to 2030 to develop 1 million EVs, an equal number of charging points by 2030. The results of this study. So that's a huge growth, and that is expected to happen with increasing vehicle ownership, as well as with a local manufacturing of an EV in Turkey, SUV type, by 2022-2023. So in that respect, the Ministry of Energy is quite interested what would be the impact on the distribution grids. So in this study, we have modeled two distinct scenarios. On the left side is a high growth scenario with 2.5 million EVs, and on the right side scenario, which there is a typo, by the way, that should be low growth, 1 million EVs in stock by 2030. I'll focus on the high growth results for this presentation. And 2.5 million EVs by 2030 is around 10% of the total passenger vehicle stock, and meaning also 2 out of 1 car that is to be sold will be an EV by 2030. So compared to today's numbers, that's quite an ambitious level. Next slide, please. What we did in this scenario, in this analysis, was to investigate the impact of EV impact and integration from two distinct angles. Also, we looked into the more support of public-based charging support, which is more relevant for Turkey, given it's a vertically integrated urban country. And in the home-based charging support, we also investigated, because currently each EV sales results in also the purchase of 1 EV charging point at homes. This is the current situation, and we have looked into the implications of that, especially during off-peak hours, when people sleep, what would be the charging implications would be. So what I'm talking about is 2.5 million EVs, 1 million charging points by 2030. So that's around 4 terawatt hours of electricity demand, roughly 2% of the current situation. And we investigated 4 grids out of 21 grids in total in Turkey. To be able to do this analysis, we have developed an hourly distribution grid model. We have received data from the 4 grids, which represents 1/3 of the total population and electricity demand of Turkey. And we investigated 4 urban and 4 rural areas, as well as the Istanbul-Ankara highway, which is the most congested highway in Turkey. And what we assumed was a 5% growth in electricity demand between now and 2030, excluding EVs. And we have investigated what 2.5 million additional EVs would impact in distribution grids. 5 charging stations have been investigated, as you also see from this graph, 2 levels in homes, 1 at workplace, and 2 levels in public places. And our power system model has the capacity to develop 16 million scenarios out of this, because there's different charging behavior, consumer behavior, there's different state of charge decisions when the car starts being charged. So this gives a significant combination, and we've boiled that down to 32 scenarios in 4 seasons of Turkey for urban and rural areas. And what we did in the next slide, you'll see that, is to look into in different urban and rural areas. So on the left-hand side, you see Ankara, urban, rural. The 3rd and 4th columns are Istanbul. Then you have Mediterranean part, the 5th and 6th. And then on the far right, you see Izmir, which is the 3rd largest city of Turkey. And these are the number of problems in terms of overloading and voltage violation in each urban and rural area. For instance, a city of nearly 20 million people, Istanbul, Kartal is the urban area which is also quite an electricity intensive region because of both industrial activity and residential density. There seems some voltage violations, as well as in Şile, which is a rural area. which is a grid quite scattered and inefficient grid. So in Istanbul, as an example from this graph, you see on both overloading and in terms of voltage violation, the EV integration had some implications. So this is the total number of problems. So 6 problems have occurred throughout the year. The number could seem big, but actually when compared to other instances where problems could occur from non-EV related causes, it's a reasonable number. What we also did in the next slide is to show this in terms of the investments. So on the upper side, you see the transformer capacity, and on the below side, you see the distribution lines. The blue bars are the current situation. The green shaded bars are the reference model where there's no EV integration, and the orange shaded bars, which are quite tiny, are when the EV integration happens, what the additional investment needs would be. Compared to the reference model, the additional investment needs for integration are between 1 to 10%. So again, in a reasonable range, 2.5 million EVs could be integrated based on this distribution grid data from 4 regions seems reasonable. And as a last slide, some policy conclusions. If you could just have the entire list. Okay, thank you. Here, of course, what I mentioned is there's currently a 1-to-1 ratio for EVs and charging infrastructure, and this needs to continue with charging infrastructure leading to accelerate the market for EVs. What we assumed here, 2 scenarios for charging behavior, home-based and public-based, and the home-based smart charging mechanisms for load management seem quite reasonable, which we currently don't have. So development and implementation of such systems are crucial. Each region came up with its own problem, so region-specific grid measures would be important to address these issues. In terms of the EV charging, what we identified, which I didn't show here, was the DC level charging stations have quite void capacity, so very low very low capacity factors by 2030. So there will be some incentives, business models needed to utilize that capacity. So there's some appetite for the market to invest in those high charging stations. Here, the 5% per year growth in electricity demand between now and 2030 was assumed, and investments will be happening in that regard. So without these investments, this 2.5 million EV integration could be problematic. So investments in distribution grids, regardless of the EV, needs to continue for this integration to happen. And obviously, there's a big synergy between distributed generation and energy storage for EV charging. And finally, this is more of a national angle, but given Turkey's priority on industry development, the benefits for industry for creating a local EV market needs to be understood in development of this results. So that's all from my side, from the Turkey perspective on EV integration. Thank you.
Thank you very much, Deger. I think fascinating. I'm sure we'll have questions, but let's move on to the next speaker first. So our next speaker is Klaus Willnow. Klaus is Head of Innovation and Future Technologies at Siemens Gamesa. Klaus? Afraid we can't hear you, Klaus.
Yes, thank you, Paul, for the introduction. And of course, thank you also for the IRENA team to invite me for this session. Yeah, my presentation, I would like to concentrate on some keywords which are in the title of this session. So may I get the first slide, please? And to start off with, I will concentrate only on the methods, how we as a company delivering wind turbines to the market can be better prepared for the unpredictable future. And for this regard, when we talk about innovation, so the first keyword is systemic innovation, we have to look into more an open approach. And our approach is here to go for open innovation, so to understand the world really as our lab instead of the lab as our world. And that is quite needed, because we do see a lot of changes happening, and therefore it is clear that the lab itself can only be the test of the knowledge. But to get the knowledge, we need to reach out to the world itself. And in times where, of course, we have a global flow of ideas around, that is even more important. Next slide, please. So what we experience is, of course, in terms of the second keyword is the consumer behavior. And we all know it's very difficult to predict what the consumer thinks. And here's just some examples how already key experts in their respective domains fail to predict their markets, considering the consumer and its behavior. Whether it will be the prediction of Daimler regarding passenger cars, or computers, or just recently, which is not too far away, the underestimation of e-commerce. So that is just some examples how difficult it is really to get consumer behavior right and to plan ahead, specifically if you are acting as a technology company where you deal with new ideas, new innovations, but you need to reflect what is really the market and what is the consumer really expecting. So if you go to the next slide, so that is, of course, some examples where we see that with regard to energy demand. I mean, we do see a major change from the centralized system to decentralized systems, and my previous colleagues already referred to this. But here's some examples what we experienced over the last years only, how tremendously we see these changes. And here digitalization comes in, of course, which has a major impact already on the energy demand. And this is driven by the change of the consumer behavior. From, say, classical libraries to e-books, or when you go from yellow pages to marketplaces, I mean, everything will be now digitalized. It's changing because technologies are available. And consumer are picking this up. So they see new opportunities in different ways of shopping, home services, mobility, etc. But what we do see on the energy demand is already a huge effect on that. I mean, we're just thinking about the IT infrastructure, the servers, and they all need energy, but also telecommunication networks, whether we call it 5G network, etc. So that all needs energy, and that is, of course, some of the drivers behind that. But this is driven by enabling technologies, what the consumer picks up. So next slide, please. So as a company, of course, facing all these challenges, it's then, of course, difficult to predict. And one way to do that is a scenario-based approach, what in this example, the company Siemens is doing, and we as Siemens Gamesa as part of that, are also trying to establish here to be more robust in our predictions. So it's a scenario work, which enables us to analyze the impact of on our core businesses. So you start to extrapolate from today's knowledge, your products and services, the technologies, customer requirements, and then you build potential scenarios in a given time frame. But you don't stop here, so you start then to retropolate backward what needs to happen to fulfill this scenario. And here in this scenario building, you include all relevant trends and discuss it in an out-of-the-box thinking. And here you do it with external experts, of course, domain experts, but also it's feasible that you include here certain consumer groups. So to get a better understanding, what are the values of the society and the individual consumers, so that you have a better picture what kind of trends are driving this. So that is one way how you could manage to better understand what's going on. I mean, it's a scenario, it's not a direct prediction, but enables us to be more secure in terms of what technologies have which kind of impact. So when you transfer it on the next slide, what we have done, of course, to draft these pictures also in regional perspective. Of course, you can drive that towards the different scopes, but here in terms of regional visions, we have created certain areas, in this case USA, China or EU, to better understand what's going on in these regions. So specifically with trends which have an impact on the electricity demand or have different magnitude in the regions, of course. But what we do see in general, and that was already stated by the colleagues, we do see an increase of the electricity overall, but regionally, of course, different. But one question is also important when we look at those regions is how much do we see a change or the need for change in the energy infrastructure, especially when we talk about the power grid. And we all know the grid connects the physical supply and the demand to the customers. So therefore, how can we find the best balance between the system or in the system for stability? So beside technologies to secure the physical connection, we need digital solutions. And here we see a strong trend of digitalization in the whole energy infrastructure. So to control the stability, but also to optimize the grid usage. What we know is that we need these technologies so that we can secure grid stability, but it offers also at the same time enough flexibility for the consumer to use different services at any place, at any time. And of course, here the challenge of decentralization is there and plays a major factor. But with this landscape building, it enables us to better understand what's going on. So from a technology supplier perspective, scenarios are very important to build up and are very helpful to estimate the impacts. But always it is that we have not one single solution to fit this all challenges. So but then we have a better understanding what trends are driving us so that we can develop technologies which enables flexibility, whatever it comes. So thank you for the presentation here.
Thank you very much, Klaus. I think you really got into the topic there. So our final speaker, before we have an opportunity for questions, and do folks please post questions for the tab. We've got quite a few coming in, but I hope we can address some of them. So our final speaker is Charlie Wilson. Charlie works is a researcher at the Tyndall Centre for Climate Change Research in the United Kingdom. Over to you, Charlie.
Great, thank you very much. So I want to share with you some empirical insights from a couple of projects I have on the go at the moment, and then explain how I think they're relevant for the scenario and modelling work we're interested in here. So next slide, please. So the first question that our panel was tasked with was to look at how the uptake of both digital and decentralized technologies impacts demand over the long term. So the graph you're looking at, each data point is an energy technology ranging from supply to end use in industry, buildings and transport. And on the x-axis, we're plotting the unit investment size, so the cost per unit of that technology. And on the y-axis, we're plotting a measure of diffusion timescale. And you can see, although there's a lot of scatter, there's also an upwards trend line from left to right, which shows that generally the smaller, more decentralized technologies diffuse more rapidly. If you look on the right, you can see a list of additional characteristics that we've analyzed, and we find that similarly these decentralized technologies tend to have lower risk, they learn more quickly, they turn over and cycle more quickly, allowing us to escape the lock-in in our energy systems. They create more jobs and are more widely accessible. Now, this is not a deterministic set of results. There are many conditions for this, but this is just to emphasize that decentralized technologies, as we've been discussing today, will form an integral part of the energy transition. Next slide, please. So this rather colorful set of app icons is designed to illustrate the kind of proliferation of digital or digitally enabled innovations available to us now as consumers, or those which are becoming available. So those on the top in blue show mobility innovations, in the middle in red show innovations in the home, and in yellow at the bottom, innovations sort of at the interface between the energy supply and our domestic consumption. Now, many of these things we've been hearing about through the course of the day. I'm not going to run over all of them, perhaps just to say the various acronyms. On the top row, you'll see MaaS, this acronym which symbolizes mobility as a service, the idea of paying for multiple transport modes through a single digital gateway. AVs is autonomous vehicles. If you look in the middle row, you'll see HEMS, which are home energy management systems. And in the bottom row, you'll see peer-to-peer electricity trading on the bottom left, and ESCOs, energy service companies, on the bottom right. Now, all of these innovations are enabled in some way, I think, by digital trends, and are becoming more and more important in our everyday lives. Next slide, please. Next slide, yeah. So what we've been doing is looking at the empirical, yeah, okay, that's fine. We've been looking at the empirical literature to look at estimates of change. So in other words, what impact does the adoption of these innovations as part of our everyday lives have on either the amount of energy services we consume or on the amount of energy we use or greenhouse gas emissions we are responsible for. And so we've been looking at all sorts of studies, from field trials to lab tests to market niche trials to some modeling studies as well, and looking at the kind of ranges of quantitative change estimates in the literature. So if you look on the left, for example, at car sharing, you see an average of around minus 25%, so 25% reduction in some quantity that is linked ultimately to decarbonisation. And if you kind of scan across the top of the row, I mean, again, the absolute numbers are not so important. What's important is the general picture that there are some interesting reduction opportunities available from these innovations. And notice on the top right as well, this work was designed well before the current crisis, but we're all becoming experts in the virtual meeting, symbolized in the top right. Now you'll notice in the autonomous vehicles box and in the bike sharing box, we actually see some numbers which are positive. In other words, the adoption of these innovations can cause either energy services to go up or energy demand to go up. In the case of autonomous vehicles, that was from a study which looked at the potential induced demand effects from making vehicles autonomous, in that if the cost per passenger kilometre drops rapidly, as may be expected, then our consumption of that service may rise. And so that's an induced demand or rebound effect. In the case of bike sharing, that very high plus 390% number is from a study which looked at people's use of bike sharing schemes and found that often they substituted for walking. And so then the energy required to maintain the bike sharing system, both in the digital infrastructure and in relocating the bikes overnight, was a net loss, if you like, for the system. So next slide. We did the same kind of trawl through the literature for the innovations we were interested in homes. And again, the absolute numbers are not important. What's important is the general picture that you get of there is clearly some uncertainty, but there is also clearly the potential for these various digital innovations to contribute to either reducing energy service consumption or reducing energy use or emissions. Next slide, please. So these change estimates, which we've been collecting from the literature, tended to measure either direct and indirect impacts. That is, direct is at the point of use, and indirect is, upstream in the electricity system, for example. There are also important embodied impacts from manufacturing of goods, for example, and also these induced demand effects, these broader systemic outcomes that I've mentioned with respect to autonomous vehicles. And as the previous speaker was talking about, there are important emissions to factor in upstream in the digital infrastructure. So this is where, firstly, none of these potential benefits which I've been outlining will happen deterministically. Importantly, policy has a critical role to help shape and steer digital innovations in the consumer sector towards decarbonisation objectives. But secondly, more relevant for this forum, is that you need kind of systems tools to capture all these various impacts of demand side change on the broader system and emissions. Next slide, please. So this is at the top is another question which we were posed in this panel. How can the tools and approaches we use to analyze consumer behavior be better captured in models and scenarios? So this, I'm going to give you an example of one scenario I was involved with a large team of researchers. It was called the low energy demand, or LED scenario. And this examined change from 2020 to 2050 in both the global north and crucially in the global south, which we haven't been talking about quite so much today. We were particularly interested in the impact of digitalization and decentralization on energy demand. And this kind of colorful wheel that you're looking at are the main elements of our scenario narrative. And Pablo, I think, explained very nicely this morning the sort of key difference between the narrative and then the modeling work that follows. So around the edge of this blue wheel, you see the big picture drivers of change, which we looked at in our scenario, what we call the mega trends. And then the brown inner circle are the more specific ways in which demand will be reshaped according to our scenario narrative. All of these things I've talked about, apart from in the bottom left of the brown circle, this term usership, this idea that digitalization enables us to move from owning single purpose goods to accessing services through multifunctional devices like the smartphones, laptops and tablets, which we're all using now. Next slide, please. So what we did is we took our scenario, we developed our scenario narrative, and we then mapped it into some bottom-up, off-model quantifications, both of the amount of energy services required and the intensity of delivering 1 unit of those energy services. So a fairly standard decomposition analysis at the energy service level. We looked at this, as you can see in the box, we looked at this for thermal comfort, for the services provided by consumer goods, for mobility and for food. And we also looked at the implications of those for upstream sectors in commercial buildings, industry and freight transport. And it's critically important to mention that we did this at the service level. So we were interested in both the potential for technical efficiency improvements to reduce the energy intensity of service provision, but we were also interested in improvements in energy service efficiency. So for example, shared ride-hailing business models which can double vehicle occupancy rates and improve service efficiency of mobility. Next slide, please. So once we'd done all the bottom-up quantifications, we could essentially tot up what the implications were for final energy demand. And globally, our scenario resulted in a 40% reduction in global energy demand to 2050. And you can see from the ruler that this is significantly below other scenarios which we see in the literature and which we've seen today as well. So really kind of pushing the envelope. Next slide, please. Now, crucially, from a methodological perspective, this was the point at which we turned to our integrated systems modeling framework. This is the message globium framework, which is widely used in the IPCC scenario community. And we use this systems model to estimate the outcomes of our scenario for warming. We found our scenario was consistent with 1.5 degrees of warming and very strong co-benefits for the Sustainable Development Goals, given our emphasis on the global south as well. Next slide, please. So this is just my final slide, really just restating the key points I've been making. Perhaps to draw your attention to the bottom, I've just been emphasizing how I think scenario narratives are well positioned to explore a very wide possibility space. And if the systems tools that we have aren't well designed to capture the impacts of digitalization on demand, then off-model analysis can serve as a useful alternative. Thank you.
Thank you very much, Charlie, and indeed thanks to all our speakers there. So I think between you all, you have really given us an excellent overview of both some of the emerging innovations and the trends, but also how we might start to understand those the implications on the energy transition. I mean, I think one thing that's been clear from the discussions that we've had so far, indeed throughout today, is that electrification of end-use sectors is going to be a big trend, but also that there's still a significant uncertainty there about which direction individual sectors will take and what the right mix of technologies and solutions will be. I'd like to unpack a little bit more with you all that uncertainty and how we understand it better. And I think some of your presentations have touched on that, but perhaps we can pack it a little bit more. So when you're considering the significant uncertainty in large-scale electrification of end-use demand, can you tell me a little bit more about how you see us reflecting that in the long-term energy scenarios? Maybe I can start with Ron as a first consideration. You talked a lot about in your presentation about the modelling of supply, but how do you deal with that uncertainty in the demand?
Yeah, so excellent question and a very challenging one. I think one of the biggest needs is for further studies of consumer acceptance and consumer behavior. In the U.S., we especially have, I think, a fairly poor understanding of how industry will respond to changes in electrification technologies. and that's a major gap. But even for transport and buildings where we have consumer behavioral models, we need much more detailed studies of rates of acceptance of different technologies, and I think so. A couple kind of places where we can learn. I think we can learn by looking at some examples of early adopters of technologies. How are they responding? What's their experience been? We can look at those technologies like space heating and understand kind of the adoption curves, which, space heating and electric vehicles that we expect to take off most quickly, and see what those adoption curves look like in the markets where they're penetrating most rapidly. And we also need to do, I think, a better job of linking and our cutting edge research on technologies with industry to informing continuing to inform our cost projections and looking at changes in market design that, of course, need to accompany the rapid transition in technologies and systems, and have to take a harder look at what are the new market and business models that will drive forward. But I think the bottom line, most important element here is really better studies of consumer adoption and consumer behavior in response to a portfolio, a plethora of kind of low carbon demand side technologies with digitalization.
Yeah, thanks, Ron. I think that makes a great deal of sense. Deger, do you want to spark off that? You were talking about your study of electric vehicles. Some significant uncertainties how consumers will behave and interact with electric vehicles, and indeed what they'll be buying in the future. How are you trying to deal with that huge uncertainty?
Sure. Actually, the results of the study which I just presented pointed at the uncertainty which is at the level of business models, and that is a question which the policymakers need to understand and provide a response. And let me try to elaborate on that. Currently, the charging infrastructure market is dominated by a few DC level and home level charging companies which produce and sell this in the market. So they just place these and sell these charging infrastructure according to how they see the market could evolve or how they think the market should evolve. The results of our study have shown that there is an important planning needed for where you place the charging infrastructure. I'm talking about especially for public based and fast chargers. Strategic choices of geographical placing has a big impact on reducing the peak load and for peak load management. So the question is, should the regulator be identifying in the future where the charging infrastructure should be placed, or should it leave it to the market? So that's one question which needs to be answered. And on the other end, there's another uncertainty, which I mentioned during my presentation, is that there's a local company, which is actually a joint venture of the 5, say, largest automotive, telecommunication and technology companies in Turkey to produce a domestic car in the next few years. So company venture, which could eventually lead into a more vertically integrated company, which could even be next to producing EVs, could also be interested in putting charging infrastructure. So that's a completely different business model, which could be dominated by a single major company compared to the current business model which we have. And these competing business models will need to, one way or another, find a way in finding the most optimal geographical choices of charging infrastructure. And this is a crucial question which needs to be addressed by the policymaker and regulators for EV integration in the coming years in Turkey. So quite an uncertain issue, not about technology, but on the business model side.
Yeah, interesting. I think that's coming through strongly. So both Charlie and Klaus, in both of your presentations, Klaus, you had the sort of bottom up and top down. I have to say the word retrapolation, was that the right word? It's not one I've often had the cause to use. But my question to both of you, and maybe I'll start with Klaus, is the extent to which you think that is sufficient to help you understand this complexity, and if not, what do we need to change? What do we need to be doing more of? Where do we need to be paying attention in the scenarios and modeling community?
Yeah, to explain it from the slides I've shown, I mean, it was the scenarios what we have set up a couple of years ago in terms of a classical forward-looking thinking. So what you know today, try to extrapolate what could be done or could be happening. Retropolate means then, for example, if you have a time horizon up to 2050, saying, okay, a certain scenario in 2050 in a certain domain, what needs to happen so that scenario becomes true? So that you can build up from today's onward, okay, what kind of steps needs to be taken so that that scenario becomes realistic. So, and that helps a bit to better understand what are the major uncertainties in these things. So there are certain things which can be judged in a certain frame, but you are able then to identify what are the disruptive things. So I can remember, for example, many years ago when we looked, of course, from the technology perspective, looking ahead in terms of the energy system, specifically when we were at the beginning of the renewables, saying, okay, when we, for example, would like to see them in 20 years and talking about photovoltaics, for example. So that was something very difficult to understand in which magnitude PV could develop. So therefore, it was a clear understanding. Photovoltaic at that time was understood as really as a disruption into the energy system. Disruption really technology-wise, but also in terms of consumer behavior and picking up things. So how the market has developed. And the same could be when we all think about storage. Storage has a character of disruptiveness to understand when we achieve certain technology steps, it can be picked up immediately by the market. And in this game between technology push and market pull, that is always then difficult to get a good picture around that. So lessons learned a bit to make the scenario approach a bit more robust is also that we tend to ask in this exercise our classical domain experts. And that might be, I wouldn't say wrong, but we will continue to do that. But it might be that we need to expand these expert groups, so-called expert groups, to others which we don't have yet on the radar. So we have to expand these so-called experts group to completely new areas, because the classical, let's say, view how we look into things is based on what we do today. Today, we know our competitors, we know the markets, you would classically ask those to a bit understand. But digitalization shows us sometimes it's happening so quickly so that we do see completely new actors. So to include completely new experts in that exercise, that is a lessons learned, I would say.
Thanks very much, Klaus. I had a similar question for Charlie, but let me expand upon it slightly. So, I mean, in your presentation, you talked a lot about sort of looking at quite a lot of this off model and then feeding that in. And my question was going to be, is that sufficient, or can we do anything more sophisticated? But I've got a question who's coming in here that I think plays to similar points. So let me read it. As several of the speakers have been saying, new technologies are somehow easy to integrate in a traditional bottom-up energy system model. But how do we account for these new business models, the market design, the way systems operate, prosumers, etc., which a number of you have alluded to? And what is the amount of soft linking and exogenous modeling needed to account for the characteristics in the energy transition? Does that make sense to you, Charlie? Can you take that one?
Yeah, my nicely prepared answer for the previous question goes out the window. No, it's a great question. I can only answer it from the perspective of the models with which I'm familiar, which are the global integrated assessment modeling tools used to look at long run climate change mitigation scenarios in the IPCC and other contexts. And because these models are by definition trying to capture the entire global energy and land use systems, they are necessarily very aggregated and coarse when it comes to representing certainly energy service level consumption and even energy demand, which is often at a sectoral level, and often demand is specified as a simple function of income and price. So the reason that in our low energy demand scenario, we did a lot of our work interested in digitalization and decentralization and demand, the reason we did a lot of that off model was because the modeling tools we were using were just absolutely not designed to ask the questions we were trying to ask. In other work, with the same modeling setup, I've been involved in trying to improve those models' representation of consumer behavior. So to give you one example, we worked on a project where we introduced some consumer heterogeneity with respect to vehicle choice. And we also did some empirical work to parameterize social influence effects. So how our vehicle choices are influenced by what we see others choosing around us. So this was a sort of incremental effort to improve the ability of that particular model to capture facets of consumer behavior which we know to be in the real world. But this is a big research frontier in the global community.
Okay, thanks, Charlie. I'm sorry to throw you off your stride there, but good answer. So we're 4 minutes away from the end, so I haven't got time to go around everybody again, but a number of questions coming in. But I'm struck by the fact that a lot of people, we're talking here about electrification, and therefore the links back to the power sector and the implications of that. People have not mentioned as much the role of gas in the energy transition and how we will understand that, and crucially the trade-offs between the role of gas and electrification. Of course, we're talking here also about indirect electrification, production of hydrogen and its on products, and the role that might play in replacing natural gas. I'm looking to any of you here, and the extent to which you've been exploring that and the uncertainty, electricity versus gas, and how we can better account for it in our modelling approaches. Any volunteers to take that one with 2 minutes to go? I'll pick on someone, if not. Ron, in a US context, have you been looking at this?
Yeah, we've been certainly looking at it to a certain extent, and it plays, of course, very heavily into questions about what will happen with heating and cooking. And we do predict ongoing low prices for gas going forward, and we include those price predictions in our modeling. But even with abundant low-cost gas, we still see significant penetration for electrification in heating and replacing gas as those technologies end up outcompeting gas going forward into the future. But we also, of course, on the power generation side, continue to see a significant role for natural gas and power generation and as a flexible source of generation for the next decade or two. So those are, I guess, a couple elements of an answer.
Thanks, Ron. My colleagues tell me that I picked too big a topic for 3 minutes just to go. So apologies for that teaser, but I'm sure this is something that we can return to in future discussions. So sadly, we're out of time there. We've got a lot of good questions coming in. We will collate those and see what we can do about them offline. Thanks very much to all my speakers. I think you gave us an excellent overview of some of the challenges and potentially some of the ways in which we can tackle it. So we'll draw this to a close. Thank you very much for joining us. I'm just checking with my colleagues as to when the next session will start. Turns out that's in 10 minutes time. So at 3:10 Central European time. Please join us again for session 5. Thanks very much, everyone.
Yeah, thank you.
Thank you.
Thank you.